Okay. You're live now, Dr. Steve.
Okay. Divided by 6 is 16 point what?
16.6.
Okay. Okay. So, Braden, make a note of how that's set up with the
Okay.
dimensions.
Okay.
And yeah. Okay, good morning, folks. Sorry for the late start. So I want to continue with some of the, along the same thing as what we got on Tuesday. And it's, oh, where's that cup of water? Ah, there it is. So, waves are vibrations. I've got a tuning fork here. I'm going to move it near the microphone for those of you who aren't here can hear it. Can you hear that? People in the class, can you hear that?
Yep.
Okay, so this is basically 256 hertz. That's a middle C. And I'm going to hold it up to the camera. If you're looking at this with the naked eye, the very tips of the tuning fork tines look a little bit blurry because they're moving back and forth 256 times a second. And I don't know if that'll show up on the video or not. Maybe a little.
Yeah.
Okay, but there certainly is vibration there. And to show that, well, if I lower this into the water, if you look closely, you should be able to see ripples.
It's a little higher.
Okay, let's do it again. Because the times themselves are, how's that? Is that high
A
enough?
little lower. Perfect.
Okay, it's actually not quite ripples because it's moving back and forth 256 times a second. So it's kind of on the splashy side, not really ripples. And in a normal classroom, I'd have a student hold this and tell them to watch for the ripples, and then we'd splash them with water. But we're not going to do that today because that means getting a bit too close. Something else that's kind of interesting is if you tap a tuning fork, and if you have access to this, in fact, I think I might just pass this around, is to get it vibrating and then look at it so you can see the blurriness. and then maybe touch it to probably the back of your hand. Might be the easiest way because the back of your hand is fairly sensitive. And you can see and also feel those very rapid vibrations. Let's go ahead and pass that around. You can grab that one side beyond the 2-meter separation. So with the yarn, you notice that we had transverse oscillations. I'm going to show you an example of longitudinal vibrations. And these are both aluminum rods. And I'm going to put some rosin, like what you use on a violin bow, on my fingers so they're a bit on the sticky side. And if I were to stroke this, because of the rosin, my fingers will stick and then release, slip and stick, slip and stick, slip and stick. And that will cause some longitudinal vibrations. And if I do this right, the rod will actually vibrate longitudinally, because I can get transverse vibrations very, very easily by just tapping an edge. And by holding it in the middle, I'm forcing there to be a node here. So by tapping on the end, the largest vibration we'll get will be where we have an antinode on each end, and I'm forcing a node in the middle. And if I grasp it a quarter of the distance from one end, I'm forcing a node here, and there'll be antinodes here and here. Would that give me a higher pitch or a lower pitch? As opposed to here. Think about the wavelength. The wavelength of the largest vibration will, in this case, with an antinode here, node and an antinode, be exactly the length of this rod. If I were to grasp it here, with an antinode here and the next node right here, is that a shorter wavelength or a longer wavelength? Shorter, much shorter, in fact. This now is going to be the half wavelength. So this rod is now going to be 2 wavelengths. And will that give us a higher frequency or a lower frequency vibration?
Higher.
Higher frequency, because rate times time equals distance. And so the rate is the speed of vibrations of this. The time is the period of the oscillation. And the distance is the wavelength. And the shorter the period, the higher the frequency, because the period is the inverse of the frequency. You've got oscillations per second versus seconds per oscillation. Okay, so this should give us a higher pitch. Do you hear that? Higher pitch, lower pitch. Now I'm going to see if I can do a longitudinal vibration. Can you hear that? Okay, and if I grasp it here, forcing an antinode there, we should expect a higher frequency vibration. This one's a bit tougher to get going. Did that, folks that are remote, could you hear that okay? There. Definitely a higher pitch.
They can hear it.
Okay. Now, if we went with a shorter rod, would you expect to hear a higher frequency here when I grasp it in the middle than what we had when we grasped the other one in the middle? Again, like with the yarn, a shorter string means a shorter wavelength. And we should get even higher still if I grasp this a quarter from one end. Okay, I don't know if I get it louder than that. Everybody hear that okay? Okay, definitely higher. And you see this across instruments. If you listen to the symphony or watch a symphony performance on YouTube or television, and musicians, I'm sure those of you who are musicians know that the instruments that are really short tend to give you higher pitch notes, and the instruments that are long tend to give you lower pitch notes. Like look at the bass, where you've got strings that are, easily this long, if not a little bit longer. That's the lowest frequency note. And you have the ultra bass, which you very rarely see, but the person has to basically stand on what looks like a ladder to be able to strum that thing. And the piccolo is very, very short. The bassoon is very, very long, and the contrabassoon is very, very long. With the brass instruments, you have to look at how many coils, because the tubing is kind of wrapped up. And with the tuba, you've got a huge amount of length. And with the trumpet or the piccolo trumpet, you've got a very short length of tubing. So it scales that way, in that the longer the instrument, the longer the maximum possible wavelength of sound you can put in the thing, and therefore the lower the pitch. Well, the shorter the instrument, the shorter that is. And I'm going to try to illustrate that with these guys. And where's the lighter? Here, over there. So let's see. So I'm going to rely on you to, since you have the intact cartilage in your knees, you want to keep that straight, try to get a gas flow. And we're going to try to, these burners, this Bunsen burner I have down here, if you maybe move it, is it showing up on the screen if we pan down?
No, Colton, you want to grab the?
Yeah. Okay, it looks like about here is about the closest you can get it. Okay. Can you adjust the airflow or restrict it more? No, not that, airflow. And keep the tube straight. Yes, that's what you want to. Yeah, close those vents just a little bit. Okay, not quite that much, back a bit. Okay, can you increase the gas flow? Okay, not that much. Back about there, okay? So basically we've got a hissing sound coming out of this burner. It's kind of burning on the floor. I don't think anybody back there, you can see it, but it's producing basically white noise. And of all that noise, some of those frequencies are going to match what we call the resonant frequency of this tube. So the hissing you see there, or hear there, is kind of akin to like the buzzing of a brass player's lips, basically producing a lot of white noise. And if we go to, really nice to have different length tubes. This one and that one are about the same. But if we go to this one, which is longer, okay, we've got a constriction in the gas. Yeah, its problem was it was lit down below. Initially, you heard a higher frequency. That's because I was exciting a, not the fundamental. Okay. Okay, right about there's where I have to have it. Okay, well, no use playing with that anymore. We have a really, can you go and try to get a shorter one? Yeah. Like we should have some about almost half this length. Okay. Now, this idea of resonance is very, very important in science, engineering, as well as music. What I have here is I have a cart with a couple of springs on it. And this is a basically a driver. It pulls at a regular rate, depending on the voltage I send to it. And just like with a kid on a swing, if you push them at a certain frequency, they're going to move at that frequency. But as you all know, there is a, oh, that's bad. Sitting there. Yeah. So you have to have that move out so it doesn't do that. Because otherwise you could burn the motor out. Okay. Actually, you can't have it so it goes out the end like that. You know how to get it? Okay. Okay, good. That'll work. Okay. So, as you remember from the pendulum experiment, there's a certain frequency at which the pendulum bob will want to move back and forth that we call the natural frequency. That's determined by the length of the string in the pendulum. Well, a kid on a swing is much the same way. They're kind of like a pendulum. And if you push it just at that right rate, you can have that kid go to larger and larger amplitudes, go higher and higher. If you're on the swing by yourself, you could basically shift your center of mass as you swing back and forth to do essentially the same thing. You know, call it pumping, if you will. And if the frequency of your pumping or the frequency of a push is just right, you can go to higher oscillations. So if you're pushing a kid on a swing, if you wait and push them, don't push them until they're right back to the maximum displacement, and then you give a push then. That means your push is right at the same frequency just as often as the natural swinging. You could, however, if you choose, apply a more frequent push. And as you can see, the cart isn't moving very much. This would be like having a kid on a swing and doing this to them. Yeah, their body is going to move at the frequency of your push, but you're not going to get very large amplitude oscillation, so that's not going to be very fun for the kid. But if we lower the frequency, we'll get closer to this resonance. And as you can see, we get larger amplitude oscillations. And I'm going to try to hit the resonance. Yeah, I think we're getting close to resonance. Larger amplitude oscillations. And if I hit the resonance exactly, well, this doesn't have much in the way of damping, much in the way of frictional forces. We can get oscillations so large it can destroy itself. I think I'm below the resonant frequency. Okay, I'm going to turn it quite a bit down from there. I know I'm well below the resonant frequency. And so we're back to not getting very large amplitude oscillations. But the danger is if you get something right at the resonance for a system that doesn't have much in the way of damping, you can have the system essentially destroy itself. That's not what we're trying to do in musical instruments. We're just trying to get something that's loud. So you apply some sort of influence, like the buzzing of the lips, blowing air over an opening, like with a woodwind. That turbulence will cause vibrations there, and whatever matches the resonance of the instrument will be amplified. Or in the case of a reeded instrument, where you're blowing air basically between two reeds. Remember the Bernoulli effect? If you blow air between two pieces of paper, they'll want to come together. Well, in reeded instruments, you either have two reeds you blow between, or you have a post that a reed can vibrate against. You blow air, past the reed, The Bernoulli effect will lower the pressure, it'll slap shut. Well, once that slaps shut, it stops the airflow. The pressure goes back to atmospheric, it relaxes, air flows again, lowers the pressure, it'll slap shut. Basically, you get a very loud and rapid clapping that produces, again, white noise. By white noise, I mean lots of different frequencies present there. And the frequency that matches the resonance of the instrument that will then be amplified. So I was actually pretty close to resonance that first time. Yeah, I think I'm getting pretty close to resonance now. And I think I'll stop it before it destroys itself. Oh, well, too late. Okay, well, you get the idea. But if you're designing a mechanical system, say if you're an engineer working on a bridge or a building, you don't want this sort of thing to happen. And there's been a number of rather dramatic and famous instances where we've had mechanical failure due to a resonance. And so whenever you have the possibility of something being able to vibrate or move, like a building swaying back and forth, or a bridge, moving up and down. How many of you walked across a bridge, like a footbridge, and found that if you walk at just the right pace, and maybe you got some folks with you that are walking at the right pace, it might noticeably start to move up and down? Well, that's something to be avoided because you found a resonance for that bridge, and you're applying a periodic force to it at that resonance. And unless there's some sort of dampening mechanism built into the structure, you might get larger and larger amplitudes that maybe the structure won't be able to handle and it could break. This is what happened to the Tacoma Narrows Bridge across the Puget Sound. And there's some very famous videos of that. They basically neglected to put in any sort of damping for a torsional sort of vibration where the bridge would actually twist back and forth. There was also a lot less damping than they should have had for vertical oscillations. And we learned a lot from then. At the time, that was the largest suspension bridge on the planet. And that really affected design of later bridges as a result. And in other structures, it's important. Another notorious example is the American Legion Hall in Kansas City, Missouri. Back about, it's been 28 years now. There was a party, basically a dance in the American Legion Hall, and they had this balcony. And there's this one song that people were dancing to that it had just the right beat that the whole balcony started to move up and down. And a rational person on that balcony, feeling that it's moving up and down when people are dancing to that same beat, would say, oh, this is very bad. I'm going to get the heck away from this balcony. But apparently that was not the conventional wisdom. Folks thought that was really, really cool and started jumping up and down at that beat because they thought the motion was really fun. Well, the oscillations got so large, the structure couldn't handle it. The balcony collapsed and 50 people died. So it's something that must be taken into account when designing and building structures. And in that case, it wasn't the design that was the problem, in that the engineers, the architects designed in dampening mechanisms to prevent that sort of thing. But the contractor who built it to save money didn't actually put the screws in right, or put in as many screws as to the dampening, what do they call them? The braces. Actually, I'm not quite sure what they were called. But the contractor cut corners, and so the dampening mechanisms that were designed were not actually properly implemented. And that caused a big problem. But that's something that's quite important. Now, let's go to that the PowerPoint slide, the first one, if we could. While we're waiting for that, I have a head scratcher, and it has not been used on heads, so don't worry about cooties. But you note, if you look at this, that there are long wires and short wires. And just like the pendulum, these wires can vibrate. Which do you think will vibrate back and forth faster, the short ones or the long ones? Which will have the faster vibration if I plucked them? The short ones, there's less inertia there. So the less inertia means if we have the same sort of internal tension, the same sort of elasticity, well, less mass means the force back to equilibrium is going to give us a larger acceleration, because force equals mass times acceleration, less inertia, less mass, or in this case, less rotational inertia. You're going to have a greater acceleration back to equilibrium, and so that means a faster vibration. But if I pluck one of these, they're all kind of coupled at the bottom through this screw, and so you're going to have vibration of one will tend to provide that same influence at that same frequency to the other tines. So if I pluck this, you can see all the longer tines now move, and the shorter ones aren't moving at all. And if I pluck one of the shorter ones, now all the shorter ones are vibrating and the longer ones aren't moving. At least not much. Did that show up okay on the, let's pass that around so you should be able to see this. So I'm trying to plucking the long ones and plucking the short ones. Oh, dang it. Braden, do you remember that the tennis balls on the hacksaw blades on the blocks?
Yeah.
Could you grab those while I start talking about this? Okay, so what we have here is another concept question. And so we've got basically a wire or a guitar string stretched, and I've got spots on it labeled A, B, C, D, E, F, G, with A and G are fixed. So those are going to be nodes. If you pinch it at point C, you can force another node there. And then if you pluck it right at B, the question is, what will happen to these riders, these little pieces of paper that are stuck on here? Will they all fly off if I pluck it very, very softly? Will none of them fly off? Will only the one at E fly off? Will D and F jump off? Or will E and F jump off? Think about what we've talked about vibrations and where we put a node or an antinode. And realize that we're going to get what's called the standing waves, like what we demonstrated on Tuesday with those springs. Think about this for a bit, please. Get your cards ready when you've made up your mind, so I can get an idea how long folks might need. Colton, Braden, do you remember who it was that spoke up earlier and answered my question about the?
I believe it was Chimidia. I don't know how to pronounce her name.
Miss Obana?
I believe so, yeah.
Okay. Miss Obana, if that was not you, please say something. Yeah. Okay, show me your cards.
She said, yes, it was. So.
Okay, good. Okay. What do we have on chat?
2 Ds, 1 E so far.
How many people are on?
3 Ds.
That's not very many.
You're at 5 Ds, 1 E.
6, 7 Ds.
Okay, so can I get a volunteer to defend why it should be D? Nobody chose A, B, or C. Can someone volunteer to defend why it's D? Sir?
I chose D because, as you explained earlier with the rods, the node is what determines the wavelength. So 2 of those wavelengths from A to C would fit in the distance from C to G,
Okay.
causing it to come down basically, or another node kind of at the point E. So the wavelength would affect D and F, causing them to jump off.
Okay, so the way you imagine would be like an antinode here and a node here.
Yeah.
And then antinode, node, antinode. So D and F should jump off.
Yeah.
Can I get a volunteer? What's your name, sir?
Josh Crossgrove.
Okay. Could I get a volunteer to defend E? That the riders at E and F jump off instead? Anyone want to speak up?
I can try to answer it.
Please do.
I was thinking E, because when you vibrate the string, I thought the most, like the, how would I say that? Like the longest vibrations or like the most movement would be viewed at the end of the string, just due to like how the vibrations travel down the string. And so I thought it would make E and F fall off because it's towards the end of the string.
Okay, so because we're going to get waves traveling down the string, we should get more effect of those waves at the end of the string because they're coming here and then bouncing maybe.
Yeah, exactly.
Okay, what's your name, Miss?
Corinne Brunger.
And nobody chose A, B, or C, and I'm just going to say right off the bat that A, B, and C are not correct. So it's basically just D or F. So let's have some discussion.
We're all in agreement.
Makes sense for me, at least. There would be nodes at A, C, E, and G because they're all spaced equally apart. So D and F would have peaks there.
Okay, so E is like just halfway between C and G, so we should get a node there and then antinodes elsewhere. Any comments on chat?
Not so far.
Okay. Okay, folks, show me your cards. Folks, hit the letters, either D or E. What do we have?
One E so far.
Okay,
Two E's.
how many Ds?
None so far.
No Davids?
One David.
How many people have replied so far in chat?
About 7, 8. So it's pretty split between E and D.
Huh, it sounded like there were more Ds the first time on chat. Is that right?
Yeah.
But now we have more E's?
Mhm.
Okay, well, let's actually do the demonstration. So I've got these spaced out. This is 1 meter long because I miscounted. I thought I had 5 intervals, but instead I've got 6. So that means I need to have 16.7 centimeters between each rider, which means I need to, at 16.7, that's right about here. So this is where I'm going to have to pluck it. And then another 16.7 right about here is where I'm going to have to hold it fixed. So well, I can clearly saw, dang it. I clearly saw that the one over here was moved, but the one over here didn't. Did that show up okay? So next time, maybe not as long. Okay, so D is the correct answer. In that by forcing a node here, having an antinode there, meant I had antinodes here, and a node in the middle. So all the riders would fly off except the one that was the next node. Okay. Now, another interesting effect is called the Doppler effect. We get this with waves, and you probably, I don't know if you ever listened to trains, but this is the classic, a train whistle. When it's coming towards an intersection that you're stopped at, you'll hear its frequency at a different pitch if it's coming towards you or if it's going away from you. You'll hear a basically shorter pitch when it's approaching you and a lower pitch as it's going away from you. That's because the sound that's being produced is basically a series of waves with nodes and antinodes. And if those sources coming towards you, well, the separation in space of those antinodes and nodes are going to be closer together, which corresponds to a higher frequency because the speed of sound is the same. But if the source is going away from you, those nodes and antinodes, those crests and troughs in the wave, are going to be hitting you less frequently, and so you'll hear a lower frequency or a lower pitch. This is called the Doppler effect. You probably heard it maybe with cars as they're honking. You'll hear a high pitch and then a low pitch or a siren if it's coming towards you and then away from you. You'll hear that yeah sort of sound. But I've got basically a speaker inside this little Nerf football on a string that hopefully we can hear that in here. So either Colton or Braden, we need to get this going.
Switch to the Allen camera.
So this is our pitch. You want to take those two and just head up the aisle. That's probably good. Okay, you about ready?
The audio is being really patchy. We can't really hear anything online.
Okay, folks, if you're remote, turn up your volume. Oops, I was too soon. Okay, for those in the classroom, could you hear that? Okay, that's good. So down here, it's pretty dramatic. You hear a na, 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 na. Okay. Did that show up at all on the L mic? Could you hear a difference in pitch?
Just a little bit.
Okay. I've got another example of a resonance thing here. Basically some tennis balls on hacksaw blades. And if I were to vibrate these back and forth, which do you think would have a higher resonant frequency? The one with the short hacksaw blade or the long hacksaw blade? Which would have the higher frequency? The shorter one.
Cool. Switch to my camera.
Any other thoughts? Mr. Crossgrove, why the shorter one?
Just as before with the head scratcher, with the same amount of inertia, it's got a shorter range to vibrate.
Okay, it really doesn't have a less inertia. Do you remember the, let's see, the blocks on the sticks? The farther something is from the pivot point, the higher the rotational inertia. So since these are different, we actually have less rotational inertia. It's going to be a lot easier to move something back and forth if it's shorter. And so they don't have quite the same rotational inertia. But having less inertia means for the same elastic tension in that hacksaw blade, you're going to get a greater acceleration back towards equilibrium in this case. And that would give us a higher frequency. So you can see how quickly I have to move it back and forth to get resonance. While here, it's less. And if I put them, together, you can see kind of a same sort of thing we saw with the head scratcher. So that's another example of resonance. Still another, and this is kind of fun. So do you have the main valve open?
No.
Okay, this one's kind of on the tricky side. Regulator is closed as well. The regulator is closed? Okay, in general, it works well to have this at the right flow from a test. And so all you need to do is turn on the big valve. Okay, I'm going to have it on kind of high initially. So we get the thing filled with gas. So we basically have some irrigation pipe here, and we're putting propane into it. And on one end, we've got a speaker. And let's see, Colton, if you could turn off the lights. Over there behind you. Yeah, there. Okay, and I think we could get by with having the door open. Okay, I think we're good. I'm going to try to lower the gas flow. Okay, that might be too high, but let's find out. And so if I play a note, the sound produced by the speaker, well, if I do the right note, we'll have a resonance. And we're going to get nodes and antinodes show up. And you see some of the flames getting brighter? You can see that where the flames are getting brighter is where we have basically a higher pressure. You can think of a sound wave as being either a displacement wave, where in some areas you got the air particles moving back and forth at a higher amplitude, and other places where they're not moving at all. Or similarly, you could think of it as a pressure wave, where you have high pressure and then low pressure. So it's very faint where the nodes are here at the high notes. And at the low end, that's close to a resonance. Yeah, that seems about the closest. So it looks like 1, 2, 3, 4 wavelengths. And that's twice the frequency, and it looks like I have 8 wavelengths. No? How many? 1, 2, 3, 4. Yeah, 8. And let's see if I double that again. Let's see if I turn that down even more. Yeah, that's probably close right there. Oh, it's good. It's up to gas, I'm losing it. Okay, do you have the lighter? Try to fill in the holes. Okay, so. Okay, I was going up and down by octaves. Yeah, that's not going to show it. And every time you change the pitch by an octave, you basically either have or double the frequency. Okay, that's probably good. And another nice thing to illustrate this whole wave superposition is think of sound waves as being like oscillations like this. I got two sound waves coming. And if they cross over so that the troughs and the crests are aligned, they should add constructively and give us a loud sound. But if they're exactly opposite, where one wave wants to push the molecules one direction and the other one wants to push them the other direction, they'll cancel out. So we can get noise cancellation going on. And that's what's happening in noise cancellation devices. They have to have a very, very rapid response, and they're only really good at lower frequencies where they got a bit more time to react. But that's kind of the principle for noise cancellation. And there's a couple of demonstrations on this I'd like to show on Monday. Remind me, Braden, I don't remember if I got on that list or not. And you can also have two sources of sound. This is a demonstration we are going to do on Monday, is if we have two sources of sound, they're both in phase, there's going to be places where the waves line up the same way, and we'll get loud sounds, but just a little bit to the side, they're going to cancel because one will want to put a maximum, a node where the other one wants to put an anti-node, and they'll cancel. So it'll be loud spots and faint spots. And any audio engineer, when they're designing like a concert hall, they're going to try to arrange the speakers so that we don't have these dead spots, that to try to avoid situations where if you're just in the wrong spot in the stands or the audience, it won't be as loud for you as it is for other folks, or that you'll miss out on some frequencies compared to others. So they try to spread the speakers around to avoid that. One of my favorite examples of resonance, though, I'm going to need the, I think I can grab it up there. It's a little mallet. In that these are resonance boxes, in that this one in particular, I think this is also a middle C. Yeah, 256 hertz. The length of this box is set to resonate at the same pitch. So this tuning fork will vibrate the box, and it'll vibrate the ear in the box. And in the box, the lowest frequency possible is where we have a node here at the back end and an anti-node here. So this distance is basically a quarter of one wavelength. And so it's set up to resonate. And so this is much louder than you'd expect a tuning fork to sound, because most of the sound is coming from the vibration inside the box. Now this one, I got little weights I can move up and down. And if I put the weights in the right place, like here, right here, I think. Yeah. By raising the weights, like with the tennis balls, you increase the rotational inertia and lower the frequency. By lowering the weights, you decrease the rotational inertia and increase the frequency. So now, if I look at the march right, this should also now be at a middle C. Yeah, that sounds about right. That sound resonated in this box and made it and the tuning fork vibrate. And there's one other demonstration I want to do with this, but we don't have the time. We'll have to wait until Monday. Thank you for your attention. We'll talk more about resonance and getting into some music